Okay. All right, now I think it's recording. Okay, so it's a little bit weird to call this chapter ketones and aldehydes because you've been learning about ketones and aldehydes for a little while. Um, you learned about like first how to make them by oxidation. You learned how to get rid of them by reduction. You learned how to get rid of them by attacking with organometallics. Um, I think that's about all of the things you've learned how to do with them. But like still, that's like a lot, and that's a really useful set of reactions to begin with. But that's not all they're good for. And in fact, carbonyls are just about what you'll be using for the rest of the class. Wait 1 second. There we go. I was looking at the wrong thing. Okay. Yeah, so I mean, for like the next, let's see, next chapter is amines, so they're not that important there. But then after that, you're going to be doing reactions with carbonyls and the carbons around carbonyls. And you'll learn like the other big class of carbon-carbon bond forming reactions, which are really useful and powerful. So carbonyls are here to stay, and so it's best to get used to them now, right? And so the way that I think we go about this is to say, all right, well, there are ketones and there are aldehydes. Okay, and we know ways of synthesizing them and breaking them down. So why don't we go down the list and think about all of the ways that we know how to synthesize or break them down. All right, let's start off nice and easy. Maybe not so easy, actually, but it's a good starting place with alkenes. So let's say that we want to make either a ketone or an aldehyde using an alkene. How should we do that?
For aldehydes, couldn't you do ozonolysis?
Yes. You could do the same for ketones too. Okay. So ozonolysis is like one of the really powerful tools we have to make ketones or aldehydes. Good. In this chapter, you also learned how to go backwards, though. You learned how to take a ketone or an aldehyde and go in this direction. This was a new reaction, and in fact, it's a super strong reaction. It comes up a lot in really, really subtle ways, or it can be very tricky to recognize when you'll need to use it, but it's a really good reaction for forming carbon-carbon bonds. So what would that be?
I think
Is that the Wittig?
Yeah, go ahead.
Yeah, exactly. So this is the Wittig reaction. Okay. Yeah, the Wittig reaction is like really a powerful reaction. The reason in part that I say that is because, for example, my final exam for Chem242 had the hardest synthesis problem that I had encountered at any point. And they told us in the problem that it was only 4 steps and it used a Wittig reaction, and like nobody figured it out. So it's a very like strong reaction. You could do some really unexpected things with it. So it's a good one to like always keep in mind. Although it doesn't get a lot of spotlight in Chem242 that much, which is kind of unfortunate. But yeah. Okay. Well, anyway. All right. Let's keep going then. So alkynes. Let's say we want to make an aldehyde or a ketone with an alkyne, and well, now it's different. So let's say that we want to make an aldehyde. What are we going to use?
Could you use KMNO4?
KMNO4.
Ooh, or would that make carboxylic acid, wouldn't it?
Yeah, I think that would cleave the whole alkyne.
I think for aldehyde, you can do the hydroboration oxidation.
Okay. So, well, if we have an alkyne that looks like this, it's a terminal alkyne, and we do hydroboration oxidation, the alcohol is going to end up on this carbon, right? And so, okay, yeah, exactly. Yeah, you're right. I was looking at my reference guide and I had it backwards. You're right, yeah. So hydroboration oxidation, and okay, well, let's be especially specific. We use a special reagent, or like one of these things that only has one hydrogen because we only want one addition. So we use like diisocyanylborane is a good one. Okay, and then if we want to go to ketones, there's like a partner reaction, or like a one that kind of goes hand in hand, which is
Mercuric ion catalyzed hydration.
Yes, it's a very fancy way of putting it. Exactly. H2SO4, and then I think you use like sulfuric acid or something here too.
Yeah, I think they used they just said H3O plus, I believe.
Okay, yeah.
But same thing.
Yeah. So okay, well, okay, we know how to work with alkynes. There's no way to go backwards to take a ketone or an aldehyde and go to an alkyne. That's like a bit complicated of reaction. In general, actually, organic chemistry here doesn't really cover how to make alkynes. I think in the book there's a brief mention about how to do it, but we don't worry about it so much. Okay, well, what about then if we want just a good old alkane? Well, what if we want to make an alkane? Going from an alkane to a ketone or aldehyde is a bit involved. That's like a multi-step process. But we can go from an aldehyde or a ketone straight to an alkane.
Let's throw some ZNH. I guess is that zinc mercury?
Ooh.
ZNHG.
Yeah, that's a good idea. Yeah, so we could use exactly the Clemmensen reduction that we learned. Or there's now an alternative, which is...
Is it the H2NNH2 thing?
Yeah. So it's the
I forgot what it's called, but...
Yeah. It's the Wolff-Kishner reaction.
Wolff-Kishner, okay.
Which is just another way of doing this. The distinction is that the Wolff-Kishner reaction uses basic conditions. So there are some times where you have things that are sensitive to acidic conditions. For example, you guys learned about acetals this week, which are good protecting groups. We'll get to that again later. But you know, if you have, for example, an acetal and you want to do a reaction on it, or if you want to get rid of a carbonyl, the Clemmensen reduction is going to screw you because it's going to break that acetal. So instead, you'd want to do the Wolff-Kishner reaction, which I believe just proceeds with hydrazine and a lot of base and a lot of heat. Okay. Cool. This is a long list, by the way. Okay, let's say we have a phenyl ring. And, well, let's say we want to go and attach an aldehyde. Okay, there's only one way to attach an aldehyde. The only thing it can look like is that. We can't do like some longer chain with an aldehyde because that's just not how these reactions work. So what was this reaction specifically called?
The Gatterman
Yeah.
Koch. I
Gatterman
don't know how to
Koch
pronounce
reaction.
that.
Yeah. I think it's Gatterman Koch.
Is that the one from like chapter 17?
Yes. Yeah, it's the one that you saw earlier. Which involves like carbon monoxide and
CuCl or
copper something like that, and then like two other things too. It's a long list of. I think you need hydrochloric acid somewhere in there, and probably AlCl3. No, you certainly can't have these two in the same room. Oh wait, no, you can. I don't think it's HCl though. There's something else involved. I can't remember what. Yeah, it's some long list. Right. Okay, and then, well, if we want to do the other side,
we could do a Friedel-Crafts, couldn't we?
yeah, Friedel-Crafts. Nice. Yeah, these are both from last time. Okay, good. You know, that's nice to have.
And Adam, for the Gutterman Koch, it's HCl. You like let that happen to form like a weird compound, then you put in AlCl3 and CuCl. What it looks like.
Okay. Yeah. Okay. So we got the right list of reagents. Nice. Kind of. Yeah. It's a long list. Okay. Now, what if we have an acid? Okay. I'm going to do something really wild here. We can go along the list. How do we make an acid out of something with like a phenyl ring? Like, let's say we have like, you know, this thing, toluene.
Oh, we've got a chapter 17 reaction.
Yeah, I know, another one.
Well, the quiz was yesterday, so I don't know them anymore, but kidding.
No. Dean, you said it earlier.
Is it the side chain oxidation thing?
Mm-hmm. Yeah. So to oxidize,
Okay,
if you ever want to oxidize the hell out of something, you blast it with potassium permanganate and heat.
Oh yes, the KMnO4.
Yeah. That's one way you can make an acid. There's plenty of other ways to make acids. You'll get to worry about those later. There's a whole chapter about them. But okay, let's say that now we want to go from an acid, and remember that these are aldehydes. So now if we want to go from an acid to an aldehyde.
Could we do dibol?
It's not strong enough.
Dibol's not strong. Okay.
No. Actually.
Is this the other one that's like dibol, the lithium, the one with lithium?
No, I don't think so. I don't think it is. So if you want to go from an acid to an aldehyde, you can't go directly. Instead, you will have to go to an acid chloride using what compound?
SOCl2.
Yeah, SOCl2. And yeah, now you use that dibol-like compound, triacetoxy. No, this one's triterbutoxylithium aluminum hydride, I think. Whatever it's called, it's this thing, right? This thing is an O-terbutyl here, right? And now this will get you the aldehyde that you want. Okay, a lot of work involved. Okay, let's go back to acid though. What if we want to make it straight into a ketone? This one we can do, although it's a little bit involved. You guys remember what's strong enough to add to an acid at all?
Is this going to be the Grignard one?
Yeah, yeah. I think so. Conventionally, I think it's usually used using organolithiums. So you might add like LIR, and you have to add 2 of them because it has to add on.
Oh, okay.
No, it only has once, I think. Oh, no. So you usually add 2 because you have to deprotonate and then you have to add onto it. But you add, and then from there you do an acid workup. So the way that, remember, this works is that, well, let's say you have O- here. Let's say we already deprotonated. Then you're going to take this guy, bump up here, bump, and then kick off this O-, although it might be OH. Something like that. And so you can make a ketone using ketone. Okay. But let's say we already did the work and we made an acid chloride, which are much nicer to work with. How could we now make a ketone instead?
Lithium dialkyl cuprate.
Yeah, exactly. So here you want to use a cuprate, otherwise sometimes known as a Gilman reagent. Yeah. Cuprates are nice. They'll only attack once. So, well, they'll attack acid chlorides because acid chlorides are really reactive, but ketones are not reactive enough, so they won't attack there. So that's good. Okay, we're almost through the list. Almost. All right, now let's see. There's 2 more. So alcohols. Okay. Is it a surprise if I tell you that you just oxidize them? I don't think so. All right. So use your favorite oxidation of choice. Swern, Des-Martin, bleach. Maybe there are others. I don't know. Whichever one you like, right? And then you could also go the other way around by using reducing agents, right? And here it's sodium borohydride or lithium aluminum hydride. Either one of those 2 will work. Okay. And we saved the best for last, nitriles, because those are new, right? You haven't been able to do anything with nitriles except just add them by SN2 before. But now you can actually do something with them. So let's say that we wanted to use a nitrile, and let's say we wanted to make an aldehyde. What's your new favorite reducing compound?
Dibol.
Yeah. This one's dibol. Yeah. Believe me, if I didn't have a reference up, I would never be able to remember these. I know, Paul, you were just saying how you had a quiz and you've forgotten everything since then. But like, this was definitely a case where I remembered these until the exam, and then I forgot about them because, yeah, the remembering dibol H, and then what was the other one we had? It was like this thing, right? Like triterbutoxy, and then there are other ones that come up later too. In fact, there's I think 2 more distinct ones that show up again. It's a real pain, and so I just remembered them for whenever I needed them, and then I forgot about them because they all do like pretty specific reactions. I think dibol H makes another appearance when you talk about acids. I think it has something to, you might be able to use it with acid chlorides or something. It comes up again like once, but But otherwise, there's a lot of these and they get kind of specific. So maybe just like make like 5 flashcards and just remember them. Okay. Well, what if we want to go to a ketone now from a nitrile? So this is where we remember that nitriles have a pretty strong dipole moment.
Could we do the Grignard?
Yeah. So you could use an actual Grignard. So first give it a Grignard, and then second, all you have to do is an acid workup. Okay. This one's actually worth maybe even thinking about a little bit, just because it's the first time that you're really working with nitriles, and well, it's kind of interesting. They'll come up again like next week. So I mean, we kind of just look at this the same way as we would look at a carbonyl, right? This is like a pretty positive carbon, and this is a pretty negative nitrogen. So if we have like a Grignard reagent, it's gonna just come in, pop up here, right? And that'll make an actual proper like formal charge. Okay, and then we'll have an N minus, right? But then when we do aqueous workup, we'll get an imine, which you also saw for the first time this week, right? But what do you know about imines in acid? They're just gonna turn into carbonyls. Whenever there's a lot of water and it's kind of acidic, imines are just gonna like disappear. So from there, we'll just get this ketone, which is nice. Okay, so here's our long list of reactions that we know about ketones and aldehydes. And this is, I don't know, most of them, maybe, hopefully. There are a few more that come up. So let's see. Maybe one of the only things that I didn't include here is that you can also, ooh, did I miss any? Oh, I did. There's one more. There's one more. I was talking about how dibol makes another appearance. This is actually where. Oh, let me not actually erase this. I'll move it. Somehow. I'm able to select. Whoa. And then move. Oh yeah. Okay. Just wait. Oh, and I need to make this one. Okay. Okay, there we go. All right, I figured it out. Cool. There's one reaction. I don't actually remember if it was mentioned in this chapter or if it's mentioned later on. But you can actually take an ester and make it into an aldehyde. This is also using dibol. I don't know if this is one that you've seen now. Or...
Yeah, can you do multiple rounds of dibol, or do you need to do H3O plus in between each successive application? Like, can you just put a ton of it in excess?
To do what?
Like, if I want to make my ester into an aldehyde, wouldn't it first stop at a ketone?
I actually don't think it would. I think it would go straight to aldehyde.
Okay.
The mechanism for this is likely just, you just have a hydride and it comes in here and kicks off the ester. Right? So I think it's just this.
Okay.
Although I might be wrong on that. Yeah. This is a reaction I didn't see it. I was like reviewing in the book today just to make sure I had everything. And I didn't see it in there today. I just know I had it in my like review material stuff from last year. So I remember that it's covered. It's certainly covered at some point. Maybe it's in this chapter. Maybe it's in a later chapter. There's chapter like 20 or 21, or one of these is about carboxylic acid derivatives, which includes esters. And so you'll certainly see this again. I just can't remember if you've seen it already or not.
No, I think you're right. Yeah, I just looked at the slides. You're right.
Okay. Okay. Yeah. Yeah, I think in either of these cases, maybe with the nitrile, you do need. Here, you definitely need aqueous workup. Actually, at least I would really bet on it. With this ester one, you might not need it. But you'll have a lot of
the slides. We're adding water as our second step.
Yeah. Okay, that makes sense. Because at the end of the day, then you'll wind up with a lot of O- and like something, right? Because you have to get rid of that part of the ester as your leaving group, and so, okay, you want to like kind of neutralize that somehow. So, at the end of the day, having some kind of aqueous workup is not a bad idea. Yeah. Okay. Cool. And maybe let me add one more, which is ethers, but not really ethers because they're really acetals, which are kind of ethers. If we want to make those out of either ketones or aldehydes, the reaction works the same way. Well, in that case, you just add an alcohol of choice. Okay. And this has to be under acidic conditions. Okay. And this is nice because acetals are good protecting groups. Okay. There are some times where you can't have carbonyls, right? What if you want to do a Grignard reaction and there's 2 carbonyls? Well, that's going to suck. You got to make one of them into an acetal, and then from there, you can proceed. But until you do, you can't really go anywhere. So this is another example of a protecting group. Okay. Pick a different color so we can make this. This is a protecting group, so that's good. Okay. Ooh, there's one more thing I can think of, and this is now actually the last thing on the list. We can also make imines, which I briefly mentioned, right? In fact, down here I mentioned them. Okay. And how do we do that? Well, you just have to give it an amine. So some kind of amine. I think it actually only needs 1 hydrogen, but I might be mistaken. And as with the reaction up here, acetal formation, this one has to be under acidic conditions. Okay. You cannot do them under basic conditions. At this point, there's like a lot of things that you could do under both acidic and basic conditions, but these, like, you should remember that they have to be acidic. Okay. Nice. Cool. All right, let's see what we got. Oh, I can't fit all of it on the same page. There we go. I don't know if you can even see all of the things on there. There's all of our reactions. It's a lot of them. But they're good to keep in mind. Okay. How about we get to some problems? Let me save this whole document. Oh. Cool. Okay, cool. So I haven't been able to upload the worksheet to the Canvas page for whatever reason. Canvas has been giving me problems. So I'm going to upload it in the chat. Okay, there we go. It apparently sent. So hopefully you found the worksheet in the chat. Why don't we start working on it? Let's see. There's 6 of us total, 5 of you guys. Would you prefer to stay in the big room or all split up? Or like split into 2 rooms, one room of 2 people, another room of 3.
I think I prefer one room.
Okay.
One group.
Okay. Yeah. Then we'll stick together. Sure. In that case, why don't I grab the first problem. And let's think about this. This is a fun one because we're starting off with the Wolff-Kishner reaction. Sorry to spoil it, but we're starting off with that right away. And this is like a real fun reaction. So why don't I give you guys a few minutes to work on it or think about this one. Feel free to talk and chat and work together on it. If anybody like feels like sharing their screen or something, you're welcome to. But I'll give you guys a few minutes. Sound good?
Yeah.
Cool.
So are we thinking we attack the carbonyl with this amine here?
I know it's going to be ketone to alkane because it's the N2H4 thing. We have OH as well, but I don't remember the mechanism at all.
Yeah, he didn't really show us. He showed us the mechanism of how it like forms an amine, but because this is a Wolff-Kishner, right? Or is it's the N2H4.
It's the N2H4. If that's the Wolff-Kishner, then it is indeed what it is.
Oh, okay. So the N2H4 is the Wolff-Kishner.
I'm gonna open the slides.
Yeah, that's correct.
Nice.
Yep.
Did he give us mechanism for that? Like, did he draw arrows?
He did, but like the first, I'm just looking at the slides too. It looks like I think this is an abbreviated thing because he wrote imine mechanism, and then he attacked with the hydroxyl group.
Yeah, he just kind of shows it from like the oxygen of the carbonyl just being a nitrogen now.
So we first have to make the ketone into an imine.
Yeah. So can we do this with just a would this just be an attack of the carbonyl group and the maybe the oxygen, like one of the nitrogens would come in, that would pop the double bond up to the oxygen, and then would that negative charge attract something to pull off the, how does the oxygen get off of there?
I think once you, like you said, Dean, like once that nitrogen comes in, the double bond that goes up to the oxygen, then it looks like you attack again, or sorry, you're deprotonating then that amine that's currently now on what is an alcohol. And those lone pairs from the NH go to the nitrogen. And I think you kind of keep doing a similar reaction until you get the amine. Imine. I don't know how you pronounce that. Is it imine or imine?
It's usually imine.
Imine. Okay.
Yeah.
Okay. So I followed you, Sophia, up until now we have a negatively charged oxygen on where like the carbonyl used to be. So are you saying, how do we?
For reference, I'm just looking at formation of imines on slide 40. But what I'm confused about here, and perhaps Adam, you can answer this, is are we just using, like, because he's saying like react we have a ketone with the primary amine in order to make the imine, and then you can carry out the Wolff-Kishner. So I don't know, like, are we adding a reagent here, or we're just going based off of like 1 and 2 here?
So we're just going off of 1 and 2. This isn't all that we need. Well, okay. Why don't we look at the imine formation, because this is like a common mechanism that you'll see again and again. So, well, like you guys said, why don't we let's go in here and attack, and what happens, right? We'll get this, and there'll be an O minus here, and an H2 plus, and H2, right? Ooh, there's a slight issue, right? This is acidic conditions, and we can't have this O minus. So it's minor, it doesn't change things, but like in terms of bookkeeping, we have to protonate first, right? So let's just be sure we protonate. Okay, okay, cool. That solves our problem. Anyway, not really relevant to what's at hand. Okay.
Oh, Sophia, is this what you were saying about how it would jump on? That's how it would be protonated. Okay, got it. Keep going on. I'm sorry.
Well, now what? How do we form the imine? Like, what's the? Don't even think about the imine so much. What's the logical next step? I guess.
So you want to deprotonate from the nitrogen?
Exactly. Right. We're doing this in water, so we can just always safely assume we have water most of the time, right? So there we go. Okay, we're like halfway to the imine. Now what can we do? In the long run, we have to get rid of this alcohol, so what's a good way of doing that?
Are we adding another one of these guys? The N2H4 to.
Ooh.
Can we protonate and have it leave or no?
Yeah, that seems like an easy way. If we were to add another one of these guys, it's called hydrazine. If we added another hydrazine, we'd have to either kick off this OH directly, but you won't have a negative charge in acidic conditions, so that's like a little bit weird. Or if we didn't kick anything off, then we'd have 5 bonds to this carbon, which is always something to look out for. But instead, Paul had a good suggestion. Why don't we just protonate? Right. Okay. So now this is a good leaving group, right? This water is ready to go do its own thing. How do we actually take it off, though?
Would we have water pick another one of those hydrogens from the nitrogen group, or from the like nitrogen immediately attached, so that we can then pull down electrons to complete the octet of that carbon connecting all of them?
Oh, okay. You could do that. Yeah.
Could we use more N2H4? Is another molecule of that?
To grab off this hydrogen, you mean?
Yeah.
Mm-hmm.
Oh, yeah, you could do that. It won't make a difference whether it's water or N2H4. I guess the hydrogene's probably more basic.
Don't we have a lone pair?
Yeah. So you could do what Dean was saying and pluck off this hydrogen, kick these electrons down, and then push this off, the water off, which works fine. And it's actually the same thing as using the lone pair, except it just is one step shorter. But, well, we have this lone pair, so we might as well use it. Plus, it's like the only reason that I'm actually going to use the lone pair here is because it's like kind of informative to see the whole process drawn out fully, right? And so, well, from there, now we get this NH plus. Oh, sorry. I was making 5 bonds on a carbon, right? Now we have to kick off this water while we do it. And then, so here we go. There's an NH, right? And there's an NH2 still hanging off the side here. And now this nitrogen is positive, right? We've gotten rid of our water. It's gone. Okay. And now we're almost there, right? We make this into a proper imine. We just take off this hydrogen. And, you know, that's nothing crazy. That's just using water or another hydrazine, whichever you like. Okay. And NH2, and then the rest of our molecule. Excellent. So we've concluded step 1.
I don't love
Very
that.
good. So this
All
is
right.
step 1. Now,
So
step 2.
let's have one of those hydroxide ions attack a hydrogen from our like primary amine coming
Up
off
here?
there.
Yeah, right. I mean, you see hydrogens, you're just gonna pull them off, right? It's like the, you know, simplest first thing you could do. So why don't we just start yanking hydrogens off, right? And H2. Well, why don't I even draw it up here? Let's say, okay, we're taking this off. Okay, yeah, let's just do it this way. So there we go, NH, and there's a minus charge here. Okay. Well, where does that minus charge go? We have to do something with it.
So now we have a minus charge. Let's also, they did a weird thing the way Dr. Tong showed the amine mechanism where you pump the double bond on, like you move the electrons that are there, you move them to make a double bond between nitrogens, bumping the double bond of the nitrogen to the carbon. So now that's an anion. And then those electrons will attack a hydrogen on a water.
Why would that happen? Because of the electronegativity of nitrogen being higher.
Oh, why would the electrons move down to the carbon?
Yeah.
Yeah. That is a good point. It's because at the end of the day, you could use these electrons and pluck a hydrogen off of water. Which gets you here. Oops. And you get that carbon-hydrogen bond now, which is really like a nice bond. That one you're certainly not going to pull off with potassium hydroxide. So this is like here to stay. Okay.
Okay, so then water.
What do we do next?
Okay, so that water has that double bond's there. Let's have another hydroxide ion come in there.
Repeat the same exact process, exactly, right? Let's take, say, use right over here. Yeah, same thing. Okay, pull off this hydrogen, kick its electrons down to here. And then, let's see. Yeah. No, we can't do that yet, I think. Well, okay, maybe let's take it one step at a time then. Here we go. It'll look something like this, right? And there's a minus here. Okay.
And don't you form, I think the way I'm just looking to at the slides, can you push, I guess, 3 arrows then? Because he was showing when that NH, when the OH comes in, it plucks off the H, right? And then the NH bond forms like kind of like a triple bond almost, but not really, because you're pushing then the CN bond to just the carbons so that you can have N2 be a leaving group.
Yeah, exactly. So the reason I was getting kind of like hesitant here was because if we move these electrons straight to here, what would happen is we'd have 5 sets of electrons on this nitrogen. That's not good. In fact, that's pretty bad. So I didn't do that quite yet. It would have been fine. It's just good to take it kind of one step at a time. So here, we're going to form the carbanion. Okay, minus charge, right? We've also formed N2 gas, which is just it's a gas, so it'll just come off, right? And, well, I don't think I need to tell you what this carbanion is going to do, right? And so this, oh, that's ugly. This is step 2. Nice and long. Yeah. So this is the whole Wolff-Kishner mechanism. Yeah, it's a long mechanism. It's also a pretty harsh reaction. So like, I mean, you really have to use a lot of base and heat to be able to do this, because you have to pull hydrogens off of a nitrogen, just like yanking them off. That's pretty tough to do. So this is a pretty intense reaction. Okay. Cool. Let's think about another problem for a bit. Grab it. It's here. Great. Okay. Hopefully you didn't think we were done with the Wolff-Kishner reaction, because there's another one here. Yeah. Okay. Why don't you guys think about this for a moment? This one's hopefully not as bad. Okay.
What are we thinking, folks? I'm feeling that ketone's gonna go away, but I don't know what else.
Are these, are we having 2 separate products? Yeah,
I
okay.
assume like
Yes.
like
Yeah.
starting material, then 2 different
Yeah, okay.
problems.
We don't need mechanism for this one, right?
No, dear God, no.
Okay.
I was
Thank you.
actually looking. I was actually looking it up earlier. Fun fact: the mechanism for the Clemmensen reduction is not yet known, despite the fact that we've known about the Clemmensen reduction for like 100, like to 150 years.
So yeah, that would make for a tough test question then.
Yeah, it would.
Elucidate unknown mechanism.
Yeah.
So are we thinking that anything outside of that ketone getting turned to a alkyl situation, anything else can happen?
I mean, from what I know about Clemmensen reduction, yeah, we're just
Yeah,
knocking the ketone
I
off.
think so. Because it reduces like everything, right?
When you say everything,
Meaning like you get like everything becomes an alkane and yeah, right?
Yeah, it's going to get rid of aldehydes too, right? I mean, the
So,
aldehydes
yeah.
come from an alkane.
Yeah.
but does it only reduce aldehydes and ketones?
I think. I don't know. I think so.
I don't think it gets rid of the
Ester.
I was actually thinking about like the aromatic compounds.
Oh no, yeah, no, it doesn't reduce double bonds of. It doesn't reduce like aromatic rings.
Right. Yeah, I don't think so.
Yeah, because we had that in chapter 17. I think I still have my notes up from on the walls here. Let's see here.
And I think, Paul, I think that we are questioning about the esters. I just have in my notes, Clemmensen is for carbonyls.
So it's not going to touch the ester then. Yeah, I don't think so either.
I don't
Okay,
think
so it leaves those oxygens alone.
That's my
Yes.
guess. I'm not sure.
Okay.
So I would just redraw the compound without that ketone, but without that carbonyl.
Okay. For which of the two?
For the topmost, the Clemmensen. I would just lose the aldehyde.
This ketone, right?
Ketone, yeah, sorry.
Yeah. Oh.
Gonna be honest, I don't like how complicated this compound is for how little's happening to it. It's kind of freaking me out.
Yeah, I know.
Yeah, I would agree with that.
Something like this.
Yes.
I think so, yeah.
Okay. What about Wolff-Kishner?
Wouldn't it be the same product? Like Wolff-Kishner does the same thing as the Clemmensen reduction. It's just safer, right? It doesn't have the mercury. So all it does is just reduce that ketone.
Okay.
Like if you're not drawing out the mechanism, it's actually pretty simple, I think.
Let's move this. Oh yeah. Oh yeah. This is advanced. Okay.
Sorry, could you repeat that? Why is the Wolff-Kishner better? Why is it safer?
Because it doesn't have mercury. It doesn't use mercury in the reaction.
Oh, okay. So it's safer from like a practical point of view, not from like a paper chem. Okay, cool. Thanks.
Yeah. Somewhat. This is like certainly not something you need to worry about. Generally safety. Mercury amalgams are actually generally pretty safe. Like for example, I don't think it's used so much anymore, but fillings for your teeth used to be made of mercury amalgams, which is crazy, right? Because you would think like, why would they put mercury in your mouth? But it turns out that is one of the things they used to use mercury for. So mercury can be pretty safe. I don't know specifically about zinc mercury amalgam. It's probably moderately safe since it's like so frequently used. Anyway, sure.
Does amalgam just mean it's like combined with another atom? Like it's like a 2-atom compound?
Yeah. And mercury, especially since it's like a liquid, is like really nice at making amalgam. Amalgam actually might be a term specific to mercury. I wonder. Great. That's an interesting question.
I've just never heard it used like that. I've just heard amalgamation used as a word.
Amalgam, a mixture or blend.
Oh, cool.
Oh yeah. Yeah, apparently amalgam in chemistry specifically means an alloy of mercury. So
okay.
it is just mercury. Yeah, and then on this dictionary page, it even says especially one used for dental fillings. So yeah, that is a big use of them.
Cool.
Okay. Anyway, all that aside, okay, cool. So why did we do 2 different reactions for this? Disregarding safety. Huh?
Because you can. I don't know. There are 2 different mechanisms to get to the same product.
Sure.
Well,
it
shows the specificity of both of these reactions that like they don't mess with ethers or halogens.
Okay.
Or aromatic rings.
True. What's like a key difference between these 2 reactions?
Oh, the Wolff-Kishner, you need a lot of heat, and it's harsh conditions.
Harsh in what sense?
You have a lot of strong base.
Acid versus base.
Yeah.
Potassium.
Yes. So here we have acidic conditions, and here's basic conditions.
Oh, okay.
So
it's like a reciprocal thing.
Yeah. And why am I spending all this time pushing you guys to notice that it's acidic versus basic conditions?
Because you can do it under either. If you're under basic conditions, you go with Wolff-Kishner. If under acidic, you go with the Clemmensen.
Yeah.
So would you do that because in basic conditions that ring with the 2 oxygens is stable, whereas in acidic conditions, it's not.
Yes, exactly. So notice that this is an acetal. Okay.
Oh, okay.
Acetals are no good under acidic conditions. They'll break. Okay. So we don't make this. Instead, what happens is we go from here. I'm just going to draw this 5-carbon ring because the rest of the molecule is pretty safely irrelevant. There we go. Okay. So we break down that acetal into 2 ketones. And from there, we do our thing.
Oh, so it would form into ketones, then it would be reduced.
Yes.
Oh, okay, so it would just form cyclopentane then?
Mm-hmm. So the products of these two reactions are different. Because here, we just have a hydrogen, and over here, we have still this acetal.
So we just destroyed the acetal. We just knocked it off the top product.
Yes. So if you were to imagine, for example, doing an aqueous workup to this now, this would be nice because we would get to keep one of those 2 ketones. Okay. Compared to in the other case where we had to get rid of that ketone because it was under acidic conditions.
So are acetals just, I like still a little fuzzy on what the definition of an acetal is.
Yeah, whenever you have a carbon with 2 oxygens, like 2 ethers, this is an acetal.
Okay.
Yeah. If you have a carbon with 1 ether and 1 alcohol, we would call this a hemiacetal. This you don't need to worry about so much until May or late April. Hemiacetals will come up again, but like not so much. Acetals though are, this we don't need to worry about. Acetals are pretty useful because you can form them really easily. So for example, let's say we wanted to make this acetal, or just generally an acetal like this. It's really common to do, let's just use this molecule, acetone. What's really common is that you might take this molecule, whose name I don't know, 1,2-ethane-diol, and then put it in acidic conditions. And so, okay, what happens, right? You add once. Okay. And then you protonate this alcohol and use this one as a nucleophile. Right. And so at the end of the day, you wind up protonating this alcohol and you wind up using this one as a nucleophile and kicking it off. Okay. And so from there, you can make an acetal that looks like this.
Okay, so just to understand a little better, one of the alcoholic oxygens is performing an attack on the carbonyl carbon, bumping the double bond up to the oxygen, but since we're in acidic conditions, it really quickly converts to a alcohol group.
Yeah. If you were writing it out as a mechanism, you'd first protonate the carbonyl.
Okay.
So you would first protonate this and then do the attack on it, because then everything always has a positive charge throughout. But it's like, that's like a minor detail.
Got it.
But
Thank
that's
you.
how you would want to write it out. But otherwise, yes, what you said is exactly right. Right. And then from there, we can go and attack.
Adam, I just had another question related to reduction. So is the only thing that we learned that would reduce everything the platinum or palladium in H2? Like even the aromatics, just so I'm like kind of remembering.
Let's see. Oh, I have a hard time. I don't know if I remember it entirely, right? Can palladium or platinum is usually what we use. Platinum H2. Let's see. Can it reduce ketones?
No.
I don't think in general. I think there are variations on this that can do it. But
Yeah, because
sure. Sophia, you might know better.
I don't know. I'm just remembering, I think he had like some office hour example and he was using like H2 and palladium and everything was getting reduced. And I couldn't quite remember like when we learned this, or maybe it was 2 steps. Like if you first did Clemenson to get rid of the carbonyls and then did a second reaction with palladium to get rid of like the aromatics. So you just had like a cyclohexane. I feel like that could probably work.
Maybe. It seems weird. I didn't think you can reduce aromatic rings with palladium and hydrogen gas. I think let's see.
Yeah, it does look, it's hydrogenation of an aromatic ketone. It looks like you can use palladium and H2 to basically do what our last 2 reductions were.
Yeah, actually, I think you can reduce aromatic rings if you like use a lot of heat and pressure. And I guess, yeah, Dean, you said okay. So you can. So I guess in that case, then it would probably work on like everything that I can think of. I know there are a ton of variations on using hydrogen gas to reduce things. There are like various compound. There's something called like Rani nickel, which is nickel with hydrogen gas like put onto it or something. That's used for some reactions.
I couldn't remember like what were these ones that could do like everything, but I'll take a look back.
Yeah, I'd recommend checking back. I can't remember when I took the class. I hardly ever used hydrogen gas and a metal catalyst. Just because wherever you can use them, you usually can use a different, more specific reagent. And like, personally, I never bothered to learn all of the places where hydrogen gas could be used. Yeah, well, there's certainly, I guess there are a lot of places. So.
Okay, thanks. Sorry for the segue. I was just like trying to think of if that compound was just a bunch of alkanes and like cycloalkanes, like what we could use, but I'll take another look, or I'll ask Dr. Tom.
Okay.
But thank you.
Yeah. Yeah, this is probably a really hard compound to reduce fully anyway, just because there's like 2 aromatic rings, and then you have the carbonyls, which are kind of like resonating with the aromatic, all that. So probably a bit tough, but.
And Adam, would you mind just quickly doing the mechanism from step 2 of this reaction here? I'm just like having a hard time seeing how we make this acetyl from this like one in the middle here.
Yeah, let's write it. Yeah, then let's write it out fully, because this is like really a good mechanism to know anyway. In part because it's like so characteristic of all of these other ketone additions. Here we go. Let's protonate. Let's protonate like that. Great. Oops. Here we go. Okay, we've protonated, and so now let's do an addition. Oops. So let's add. Okay. Okay. So now there's a plus charge on this oxygen, right? Well, let's just get rid of that, right? We have water floating around. And okay. So now we're at step, we're here. We're good?
Yes.
So now what? Okay, well, we repeat. We're going to protonate here. All right. So let's protonate. There's a plus charge on there now. Very good. Okay. And now I've just rotated this part of the molecule to be over here, so that it's in a nice position and I could actually draw it attacking. Okay. There's a lone pair on this oxygen. It's going to act as our nucleophile. So we just do good old SN2 here. Okay. We get rid of that water that we make just because we don't need it in anymore. And now we've formed our whole ring. But there's still a plus charge, and so we just take care of that by bringing in water and deprotonating. There we go.
Awesome. Thank you.
Yep. Using this 1,2-ethane diol to make acetals is a really common thing. This is like a frequent thing used to make acetals. I think just because it makes acetals really easily. I mean, making a 5-membered ring is like really energetically favored. And also, I mean, you just have like this other oxygen right here. So like it'll happen fast just because everything's near each other. So it's like a good reaction. Excellent. All right, I'm at the end of the page, so let's make a new document. Oh, yes. Okay, good. All right, let's get a new problem.
It's funny, the next problem is using the diol, but we're in basic conditions now.
Oh, but the first step has toxic acid. So that's all
sorry.
good. Yeah.
I always get confused when I see the OH.
Yeah. Yeah, it's a bit weird. Nobody ever like tells you about toxic acid. You learn about tosyl chloride and like TSCl or like O-tosyl groups, right? And nobody ever makes you think like, oh, toxic acid is like a pretty good acid because, I mean, remember the whole point. The whole reason this is a good leaving group is because it's so good at resonance, right? So if you stick a hydrogen on there, that hydrogen will come off really easily because of, again, resonance. So this is actually like a pretty good acid, I'm pretty sure. Plus it's like easy. I'm pretty sure organic chemists have a lot of it around all the time. So it's a good choice. Yeah. Okay. Why don't you
So
guys
would
think
we
about this briefly?
form just 2 acetals here? Kind of poking off of the chain.
Ooh, okay. But there's only one equivalent of toxic of the diol.
Oh. Don't we talked about this in the? Is this just have to do with the reactivity of ketones versus aldehydes?
God. What do the rest of you guys think?
Yeah, my first thought is kind of like which one would become the acetal here. And I'm not quite sure.
With one equivalent, your aldehyde is gonna react faster than the ketone. So the aldehyde will become the acetal first. So that's why you can use it as a protectant group, is because it will react with aldehydes before ketones. And then, right, this is what you can get rid of like super easily with just dilute acid.
Yeah, exactly. Cool. So we make the acetal, and it's on the aldehyde, right? Because in general, aldehydes are more reactive. So we have one acetal and exactly one acetal on our molecule. Okay. And now, what is this step?
Okay, so we are then doing. Would we call this dilute acid conditions, or what would you call that? Because it's slightly more acidic than regular, right?
It's acidic.
All right.
Yeah.
So imine formation.
Okay. Yeah. Remember, imine formation always has to be acidic. And if we have a carbonyl and an amine, well, no reason the two can't work together. So yeah, why don't we form the imine? Okay. Cool. Here's a reagent you haven't seen before, but maybe you could guess what it does.
It throws on a nitrile.
Ooh.
Maybe.
Not in this kit, not in the imine, no. Actually, no, it doesn't use the nitrile that's on there. That's a bit misleading. Yeah. Think about what else it might do. Well, that was a good suggestion for having never seen this reagent before that I didn't expect.
Is it a substitution or elimination? Because it's a salt. It's an ion.
Either. Does this part make you think of anything? Anyone?
Is it gonna
I can
make
tell
our,
you.
Reducing agent?
yeah, is it gonna reduce our amine?
Yeah. Yeah, exactly. It's a reducing agent, which, again, you will see. I guess this week, because this week you learn about amines, and if your head hasn't already fallen off, it will this week, I assure you.
That's good.
Yeah, yeah.
This is all chapter 18?
Except this reaction is chapter 19, but otherwise everything else is chapter 18.
That's not great.
Yeah. Yeah, there are a lot of reactions. It is hard to keep track of all of them.
Do we should we be familiar with mechanism for everything, or mostly predict the products?
There are a few things that are like really common mechanisms that you should know, like acetal formation. Definitely know. Wolff-Kishner, you should know. Well, I mean, as always, it depends on what Dr. Tong has said you should know. But like,
Yeah.
Those are both things that I would say you should really know. I can't remember what other major reactions we've talked about. Oh, the Wittig reaction. The Wittig reaction is one that you might want to know the mechanism for if he covered it in class. Also, knowing how to make the Wittig reagent, because like you want to be able to actually make the reagent so you can use it. That's also important.
Okay.
Yeah.
Is that what we went over in the beginning of class? The formation of the Wittig?
We didn't talk about it today.
Oh, okay.
No, we haven't. It's a kind of cool mechanism. It's like a neat thing. It is in the book, so if you're a book fan, it's on there. Yeah, there are probably other mechanisms too that maybe I'm not thinking of. Imine formation, certainly one that you should know.
I guess, Dr. Tong does have those like intro slides where he tells you what you should know. So I think if I were less lazy, I should just look at that and figure it out from there, as opposed to asking you.
That's pretty reasonable. Yeah. Yeah, see what's on there.
So in the next step, is our H3O plus workup just gonna protonate our amine?
Oh wait, and since it's acidic conditions, won't it also revert our acetal to a cyclopentane?
Yeah, or the acetal, it'll revert it to just an aldehyde.
Oh.
Yeah.
Wait, but when we talked about that last reaction with the crazy compound, didn't we make it a cyclopentane?
So remember the original the molecule that we were working with in the other problem looked like this. With some craziness. Okay. And so if we removed this acetal, then, well, plus. So we're keeping this top carbonyl, right? Because that's fine. And then we're making a carbonyl down here.
Oh, okay. I guess I wrote the.
Yeah. In general, when you have an acetal, like this, right? And then whatever else, you could just think of it as taking like this bond and this bond and just making it a carbonyl instead.
Oh, okay. Got it.
Yeah.
So just a quick thing. So we were using that amalgam also with zinc in that previous problem. So wouldn't both of those ketones be gone? So it would just be the like benzene attached to cyclopentane attached to that phenyl group.
Yep. Exactly. So the product just looked like this.
Got it. Okay. Thank you very much for clearing that up.
Yeah. It's worth mentioning that acetals aren't the only thing that you can kind of think of like just really quick and dirty like this. You can also do the same thing for like, I mean, imines are the same way, right? If we want to make an imine, then you don't have to think that hard about it. All you do is just replace what's on that double bond with whatever your imine is, right? This is provided that we use like NH, I don't know, 3 or whatever.
So for that previous problem, sorry, the one with the bicyclic molecule, we don't end up with our final product with a ketone after we treat with H3O+. We lose the acetal, but we end up without a ketone.
Yes. Yeah. It's because the acidic conditions come from the HCl, which is part of the Clemmensen reduction. So you use that acid to first get rid of the acetal, and then you're doing a Clemmensen reduction in the same reaction. So you just do the Clemmensen reduction from there.
But that's not true for the Wolff-Kishner. The Wolff-Kishner will leave us with a ketone.
It actually won't even leave us with a ketone.
Because what I have written down for my product for the Wolff-Kishner pathway was a ketone on the bottom.
So I just added this step, like extra.
Okay, yeah, that's a workup. All right.
Yeah. If we wanted to work it up, we could, but we don't have to.
Okay, cool.
Yep. Okay. Yeah. Okay. Oh yeah, and then also with this whole like thing, like let's say that we have a carbonyl 2, and also let's say we're doing a Wittig reaction, right? Which looks like this. Okay. Or I think sometimes it's drawn with a double bond. Whichever one you've seen used, you should use. This is another situation like just, don't overthink this and replace the oxygen on the other end of that double bond with your carbon. Like that's the really nice thing about the Wittig reaction is that it's just like just replace the oxygen with whatever carbon thing you want. Put anything on there. So that's quite nice. Same thing with imine formation. It's just like to replace the oxygen. And with acetals, similar thing. Replacing the oxygen. So that's a nice thing. Okay. Anyway, this amine could be protonated. It might not be protonated. Whatever. Doesn't make a difference. Okay. pH 5.
Would that just be like acid catalyzed hydration of that aldehyde on the end there? Like you'd end up with a carboxylic acid, I guess.
That would be oxidation.
Oh, okay, gotcha.
Yeah. That wouldn't be it. pH 5 is probably, yeah, you could form an acetal on that. Like you could just stick water on here, right? So yeah. So this is one option. You could do this, but this isn't very likely to happen. There's a much more likely reaction that'll happen. What do you guys think that is?
Would we make an imine?
Yes.
So it would be
Yeah.
like molecular, right? Because you have both of them on that chain.
Yeah, exactly. And one way that you might realize that is that earlier it said pH 5 when we were making an imine, right? So if it says pH 5 again, it's like the same step. So yes, we're going to make an intramolecular imine. Okay. And like with what I was just saying earlier, we don't want to think that hard about this. And so the best way for us, oh, sorry, I've missed some carbons. The amine that we used all along had some extra carbons, right? It looked like this and then this. It doesn't make a difference, right? It's just nice to include those. Here we go. Okay. So yeah, we're just making an imine. It's intramolecular. Cool. And we don't want to think that hard about this, right? So we're just gonna, we know that at the end of the day, we're going to replace this oxygen with a double bond to a nitrogen. Okay, which is this nitrogen. Okay, and it's gonna make a ring and it's gonna be ugly, but what we can do is just say, all right, well, there are 1, 2, 3, and 4 carbons here. And then this nitrogen can be like the 5th thing that'll make the ring that we're gonna be making. Okay, so what's our final compound gonna look like? It's gonna be, here's this stuff on the side that we're not that interested in. There's our nitrogen, right? There's carbon 1, no, this was carbon 1. There's carbon 2, 3, 4, and 5. 5 is the nitrogen itself, okay? And it's a double bond there because that's where we just replaced the oxygen. Okay. And one last thing is missing. Who knows what that is?
Water? We produce water?
No, there's nowhere to put water on here.
I mean, we lost our oxygen, right?
Mm-hmm. Oh, yeah. Okay. So we lost water in this process. But there's something missing in this structure that we must include. What's going on with the nitrogen?
You have a positive charge on there?
Yeah, exactly. Okay. Yeah. We can't get rid of the bond. We can't get rid of these carbons, right? When we're making a normal imine, if this was an NH2 here, like I was writing earlier, then we would have just been able to pluck off those extra hydrogens, and we would have a neutral amine. But in this case, we have to have it with the positive charge at the end because, well, we can't get rid of that carbon chain. Okay.
I have to hop off a little early, but thank you so much,
Okay.
Adam, for today.
Yep. Bye. Yeah. Can you send your pen ID number in the chat, like DM it to me?
Yeah.
Or something? Just, yeah. Yeah. If the rest of you want to do that too. It's cool. Here, let's get an extra problem. Extra 2 problems. Very exciting. Nice. Right.
I may hit art as well, but thanks so much as always.
Okay. See you. Yeah. Dean, you
All
want
right,
to
I
stick
guess
around?
it's just us and Adam for the last 15.
All right. Yeah. Well, let's go through the rest of them then, or however many more we can get through.
Perfect.
Yeah. These two are fairly short. That's nice. Yeah.
Okay, so with Swern, is it always that really weird looking like dichloride reagent? Or what goes into the Swern oxidation?
This
Yes.
guy, oxalochloride, DMSO, triethylamine, I hope. And then that might be it. Maybe water? I can't remember. There's also no reason you'd have water and DMSO in the same thing. So maybe not water. This is probably it, I think.
Perfect. Okay, so let's throw. Okay, so that's just a cyclohexane. An alcohol here. We had an ester. Okay. All right. So does it replace the carbonyl of that ester with a chlorine?
No, it wouldn't do that. No, that would be complicated and there's no need.
Okay. So then let's see. Oh, it turns alcohols to ketone. No, aldehydes.
Yeah, in this case, an aldehyde because it's on the end, right? It's a primary alcohol, so
Mm-hmm.
just an aldehyde here, and then you leave this ester alone. It's not bothering anyone. Well, really, it's already oxidized. It's actually what it is, but also not bothering anyone. Okay.
Awesome. Okay, so we have that. I'm just gonna draw that product real quick. Okay, so now.
What
There.
reaction are we going to be doing with this thing?
Yes. Didn't we just played with this, didn't we?
Yeah.
This will replace carboxyl oxygens with our group, right?
Yes. Exactly.
So then
what is the R group?
the R group is propane.
Yeah, exactly. Right. So we're splitting here. And let's say we have one equivalent.
Oh, we know aldehydes are more reactive than our ketones.
Oh yeah, we do. Yes. Yes, they are. And so
if
all that we're going to do
yes,
is just remember swap these double bonds, right?
mm-hmm.
That's it. So do I have the right color? Yeah, I do. Okay. Well, here's a hydrogen, right? And we keep our double bond, and we need two things on this double bond. What's on one side of them and what's on the other?
On one side is a hydrogen.
Okay.
And then on the other side would be our 3 carbons or propane.
Like that?
Yes? Or would
Okay.
it be trans? Does it matter?
Oh, shoot. I can't remember. One of the two is preferred. I think trans is slightly preferred. I can't remember, but this is something that would be good to remember.
Let's see here. I think I do remember him saying something about slurn here.
Yeah. Oh, I used to know this.
I mean, isn't usually the trans preferred?
Yeah, I think so.
General rule. Reduction.
Okay. The book is kind of lame, and the book says that you get a mixture.
Oh, okay, that's less fun. But so we just get both.
Yeah. Okay.
So throw that.
Okay. Does this product look good the way I drew it?
Yes. Does it look good to you?
It's a little bit off.
Oh, something's wrong. Okay.
Yeah. It's subtle.
Okay, let me think. So it has to have something to do with what we did here. Yes. Yeah. Okay. So if we're adding this double bond, okay, so nothing's gonna happen to the carbonyl carbon because it still has the same amount of bonds. Would it be the other side of our alkene here? Is something's up?
Okay, yeah.
Would it have? Oh, is there a negative charge on the first carbon of that propane? Or no, positive?
No charge. the Wittig reaction is really nice. It's clean. It gives you a nice product right away.
Okay, let me see.
Yeah. So we're going to use the oldest trick in the book here and just count. So our Wittig reagent had 3 carbons in it. And here we've added 1, 2, 3, and 4. Right.
Get rid of the 4th carbon?
Yeah.
Gotcha.
So that is something to be careful about. Yeah.
Okay, got it. All
Cool.
right. So, and
Okay.
so that is it for that one. H2SO4. Okay. So H2SO4 to carboxylic acids. Let's see here. So it's just an acidic, basically, this is what's interesting. So it's like you have acidic hydrogens, but it's also like a basic solvent. I have no
Yes.
idea what.
Okay. Well, what have we been talking about with alcohols and acidic conditions
Okay,
all this time?
let's see here. During this, we did a reaction earlier where we used that. We would have our carbonyl oxygens attack the proton, which then allows a nucleophilic attack by the oxygen of that alcohol. So we're basically going to end up, we're going to form acetals.
Yeah.
Okay.
So,
And since it's solvent, we have plenty of it. So will it happen to both carbonyl oxygens?
So it'll happen down here for sure.
Mm-hmm.
Because it's a ketone and that's, it's nice and easy. Up at the top, it actually won't happen. You won't form an acetal. And the reason for that is because, I don't know, well, let's say we tried it on here, right? So we would protonate this carbonyl. And then we'd have to like attack with this alcohol or this water. And then we'd get 3 alcohols on here, and that's not going to work.
Yeah.
Right. And let's say, okay, what if we were to take one of these alcohols off, right?
Mm-hmm.
Then we would just wind up with like this, right? And then we would just kick these electrons down. And so, okay, we'd get an acid again. Waste of our time.
Don't you also never really react with like you never like add a tertiary alcohol? Isn't that something?
Yeah, exactly. That too. You like never get this.
Got it.
That doesn't really happen.
Okay.
Okay.
And like you said, you would just get back to where you were, even if it could happen.
Yeah.
Okay.
Yeah, it wouldn't get you anywhere. So that's not going to work.
So we form a nice acetal right where our ketone used to be.
Mm-hmm.
And
do we still have a carboxylic acid? What happens though? This is not the final product. I'll tell you. There's more.
So also, is that thing on the left an acetal?
Mhm.
Okay.
Yeah, it's just ugly.
All right, no problem. Okay, so ketone or an acetic acid when exposed to these acidic conditions. Would this become an aldehyde?
No, this is not. These aren't reducing conditions.
Oh.
Actually, reducing a carboxylic acid is pretty hard. You would need a lithium aluminum hydride to do that. I don't really think in one step there's like no other way to do it that fast.
Okay.
Yeah. Let's forget about everything else on the molecule. What if I just write this?
Would the proton, would the oxygen on the carboxyl or like the OH group coming off the carboxylic acid, would that oxygen attack a proton?
This one?
Yes. Or would it be more likely that the okay, so the
It'll be
carbonyl
this one up at the top.
Okay. So carbonyl oxygen will attack a proton. And that will lead. See, but now I'm curious because it seems like where my mind's going is where we were at a second ago, where we just have 3 alcohols somehow attached.
Okay. Yeah. So that's actually a good thing to think about. Let's say we do that, right? And then what's going to happen is we're going to do exactly what we did earlier, right? We're going to have 3 alcohols attached. Except it's not 3 alcohols. It's 2 alcohols and an ester.
Oh.
Right. Or an ether, right? And so let's say we kick off one of these, right? We lose that because we form the carbonyl again. Right, and now we deprotonate. We've made an ester.
Interesting. Okay.
Yeah.
Oh, so this is going way back to ester synthesis.
Yes.
Oh no, I don't think we've done ester synthesis yet.
Really?
Yeah, we haven't.
Have you heard of the term the Fischer esterification?
Yes. Okay. So, all right. Touche.
Yes.
We have done.
Yeah.
Okay.
Yeah. Yeah. I know this is a problem from a past exam in like somebody's class. And even when I was taking the class, I think it might have been when I was taking 241, but I can't remember. There was some problem like this, and it was really nasty. This is not as bad. So anyway, this final product, like, you know, is just. I'm not gonna draw the ring because I'm too lazy. It just forms the ester, right? Yeah, when I was taking the class, there was a really nasty problem. It wasn't that hard at the end of the day, but like it was a mean problem because it was something like this, and then there was this ring, right? And there was like a chlorine and like a CO2H, and then it was like, oh, what happens if you give it like ethanol? and acid, right? And then like everybody put, oh, like you're just gonna make an acetal, right? And then nothing's gonna happen on the ring because it's a ring, right? You can't react with that chlorine, or you like can't do this, right? But that's not correct because this is a carboxylic acid. So you'd also do a Fischer esterification.
Oh, wow. Okay.
Yeah. So they like when I had this problem, it was really sneaky because they wrote it as CO2H so that nobody would notice or think about it, but like it was there.
Yeah, but since you do have that carboxylic acid, you're able to do the Fischer esterification. Okay.
Yeah. And so this would actually come out as this.
Mm-hmm.
This is sneaky.
Got it.
Yeah.
Okay, awesome. Now I know there's plenty to review for Friday.
There's always a lot to, yeah. There are like a million reactions in this section, so. Yep. Okay.
Perfect.
It's
All
around
right.
1, so
Yeah.
I'll let you
thank
get
so
on with your
much.
Sunday. Cool.
Perfect. Well, pleasure as always, and I will see you on Sunday.
Yep. See you next week.
Yep.
Bye-bye.
Have a good one.